Okay, task 6 is another CSG tally, and this is DPA, or displacements per atom. So here's a displacement, or a few displacements of atoms caused by a primary atom, which zooms in at high speed. What this video doesn't show you is the recombination that can happen. So there will be an original displacement of atoms, and you might have a wonderful cascade of damage which could look something like this. And then depending on the material properties, whether it's a crystalline, whether it's a liquid, the temperature of it, a certain fraction of those atoms, anywhere from a small number to 100%, will return to their original locations. So the neutron simulation is able to tell you the original magnitude of the displacement. It's not a material science simulation, so it's not able to tell you the recombination effects. This task goes on to do stochastic volume calculations, because although the neutronic simulation is able to tell you the total number of displacements in a volume, it needs a little bit of help calculating the volume. So the method it uses is to randomly generate particles within a known size cube of length s. And it knows that the ratio of particles in the cube to particles in the sphere is the same as the volume of the ratios. And because we know the size of the sphere is radius r, and the cube has length s, we know this will refactor to 6 over pi. Let's assume r equals 1 and s equals 2. So you could do this with a more complicated shape. So here we have a first wall with a hole in the side and some corners, and we don't know the volume. But what we could do is put it in a box where we do know the volume of the box, and we can generate maybe millions of particles randomly within that box, and we can record the particles, or tell the neutronics code to record the particles that arrive in the cube to those that arrive within the shape. And then you can get your overall volume. Now I'm just going to run the workshop and open up this URL, and here's the workshop and task number 6 and DPA. Now the last task was on TBR, so we kind of glossed over these settings for the particle simulation. In general, this is the computational intensity. So we have a few important numbers here. The batches and the particles are the two I'd like to talk about. Inactive, we always set to 0 for fixed source simulations. You need that for criticality simulations, but not for fixed source. So, batches and particles. What is a batch and what is a particle? And how do they change the number that you get? To understand this, we're going to do a simple dice rolling experiment. And we're going to record the results on a spreadsheet. So, if we roll it, we will get a number of 2. Roll it again, and 6, and I'll roll it a few more times. Okay, I've rolled the die 10 times now, and I should point out the name of this game is to find the average value of a die roll. So, that's easy to do, equals sum of all of these numbers divided by 10. Simple. So, the average on this little experiment, let's call it experiment number 1, is 3.3. That's great. I have little idea about the error on that, so one way of finding that out is to do a second experiment, or a second batch. So clear the history, and we'll do a few more die rolls. Okay, I've come to the end of the second experiment, and I got a mean of 2.8, and I could repeat that for a few more experiments. Here's my dice roll history. Okay, I have done a few more experiments now, and I am going to work out the average of all of those experiments. So this would be particle 1 for batch 1, particle 1 for batch 2, particle 3 for batch 3, and so on. So in this case I've got 8 batches, 1, 2, 3, 4, 5, 6, 7, 8, and I've got 10 particles for each batch. And this will give me 10 different results. So I still don't know what my final neutronic simulation result is, so to find out the final answer, you sum them all up and divide by the total number of batches. So my final answer is 2.975, and I have a standard deviation on that of 0.25. So that's what the batches and the particles does in a simulation. You can improve your accuracy of your answer by increasing the number of particles per batch. So I could have 100 particles per batch, or I could improve my uncertainty on the experiment by increasing the number of batches performed. Both are useful, but some of these simulations are limited just to reduce the simulation time. So that's great. We understand materials and geometry, and now we understand settings, and we understood the source already. Tallies. So a tally is telling the neutronics code what to record. In this case, we're telling it to score 444, which is a particular MT number. You can find all the MT numbers in this OECD Handbook of MT Numbers. And if we go all the way down to MT444, we'll find that it is not in there, but it is DPA. You can believe me on this one. Others which are useful for us are 205, which is the total tritium production. And in this case, X is a wildcard, so it produces, it could be a neutron there, it could be nothing there, but as long as there is tritium in the output channel, it is MT205. So the rest of the task goes on to do a stochastic volume calculation, and ultimately you find out the DPA of a material that you've irradiated. Okay, good luck with task 6. Thanks for listening.